Hello everybody, Namaskar. So in the previous lecture I have discussed on cycle configuration based on the multi-stage compression with intercooling. Now in this lecture I will discuss the second type of cycle configuration for the multi-stage compression. Okay, so this cycle is the multi-stage compression with flash gas removal. Okay, so two-stage compression with flash gas removal I will discuss in this case. So here also we are using the two compressor, and in between the two compressor system we will change slightly in a configuration. So in this case what we will do that we will maintain some intermediate pressure. Okay, so where we will use the flash chamber, and in a flash chamber that will operate at the intermediate pressure. So that pressure in between the low temperature compressor to in between and the high temperature compressor. So in this intermediate pressure basically we will use the expansion process 5 to 6, that is the first expansion, and that after that we are getting the liquid and vapor. So here flash chamber is basically used to separate the liquid and vapor. So vapor at 0.8 and liquid at 0.7, then again that only liquid that is going to the second expansion devices. So that means the 7 to 9, this is the expansion process in a second expansion devices, and the 7 is basically the liquid of the flash chamber. So then that two phase mixture at 0.9, this is going to the evaporator, and then after the evaporator 1 to 2 is again the compression process in a low pressure compressor, and then at the intermediate pressure the vapor at 0.8, that is basically mixed with the vapor which is coming from the low pressure compressor, and both are mixing together in the mixing chamber, and then we are getting the 0.3. this is also the superheated vapor condition. So this then that is going to the second compressor, high pressure compressor. So that compression process is 3 to 4. Okay, so here basically we are using the two compressor, but the in between the two compressor, so again we are basically getting the intercooling, but this intercooling is not due to the external intercooler. So this intercooling we are basically getting due to the vapor which is coming from the flash chamber. Okay, saturated vapor which is coming from the flash chamber. So after the mixing process, so we will see that in the temperature that T2 that is the temperature after the first compressor, but that state point is changing to at 0.3. Okay, so the temperature T3 that is always lower as compared to temperature T2. So basically this is also one type of intercooling in between the two compressors. So the first, after the first compressor, after the condition we are getting, then we are getting some intercooling. So that means the temperature of the refrigerant after the low pressure compressor, that will be decreased in a mixing chamber, and we are getting the temperature T3. Okay, so this we can represent in a temperature entropy and the pressure enthalpy diagram. So we can see that the 5 to 6, this is the expansion process in a fast expansion devices. Then in a flash chamber that the liquid, that means at 0.7 and vapor at 0.8, both are separated, and liquid is again expanding in a expansion devices from 7 to 9. Then 9 is the inlet of the evaporator, then 9 to 1, this is your heat addition process in the evaporator. Then 1 to 2 is the compression process in the first compression, and that vapor at 0.8 and vapor at 0.2 are mixing together. Then we are getting the state 0.3 in between that. Then the 3 to 4, this is the compression process in a second compression. Okay, so for this case the 1 to 2s is the isentropic compression process, and also the 3 to 4s, this is the isentropic compression process in a second compressor. So same thing we can represent in a pressure enthalpy diagram. 1, 2 is the compression, then the 3 is the that is the after the mixing, 0.3 we are getting after the mixing, then 3 to 4 is the process in the second compressor, 4 to 5 is the heat rejection process, 5 to 6 is the expansion process in the first expander, and 7 to 9 is also expansion process in the second that expansion devices. Okay, so for this case now we can do the calculation for this cycle. So that calculation process is very important. So here basically I will discuss only the calculation procedure, how we can do the calculation by using the table, saturation table of the refrigerant. Okay, so for any refrigerant, if the saturation tables are given, and in a saturation table the saturation properties at the defined temperature or defined pressure, okay, that means the saturated vapor point and saturated liquid point, if those data are given in the saturation table, then by using that saturation table, how you can get the enthalpies at the defined point of the cycle. Okay, so that we will discuss, and after getting the enthalpies at defined point of the cycle, finally we can calculate what is the performance parameter of this cycle. Okay, so this is the main theme of the calculation procedure. So in this diagram, temperature entropy diagram for this cycle, we can see that if the three pressure, for this case also, if the three pressures are given, one is the evaporator pressure, other is the condenser pressure, and third is the intermediate pressure. If these three pressures are given, then we can see that 0.1, 0.8 both are basically the saturated vapor point. Okay, so 0.1 is the saturated vapor at the evaporator pressure, and 0.8 is the saturated vapor at the intermediate pressure. So 0.1 and 0.8 we can get from the table, and then the 5 and 7 both are basically the saturated liquid points. So 5 is the saturated liquid for the condenser pressure, and 7 is the saturated liquid for the intermediate pressure. So that the enthalpies or property at 0.5 and 7 both we can get from the saturation table. So then the 5 to 6 and 7 to 9 both are the isenthalpic processes. So the enthalpy at 0.6 and 0.9 also we can get. Okay, so now apart from this, if you want to calculate the process properties at 0.2, so 1 to 2, this process is the compression process. So the calculation procedure for this state 0.2, that will be similar to the previous cases which we have discussed. So initially we have to assume the isentropic process 1 to 2s, then we have to calculate the enthalpies at 0.2s, and then by using the isentropic efficiency of the compressor we can calculate the enthalpy at 0.2. So now the state 0.3 we have to calculate. So to get the state 0.3, we can use the that energy balance or the that liquid vapor separation in a after the first expander. Okay, so first expansion devices. So that means at 0.6 we have to calculate what is the dryness fraction. Okay, so at 0.6 the dryness fraction, that is basically the vapor portion, that x6, that is represent the fraction of vapor portion, and the 1 minus x6, this is represent the fraction of liquid portion. Okay, so for the unit mass flow rate for the condenser or 5 to 6, we can say that the x6, that is the represent the mass flow rate for the mass flow rate at the 0.8, and the 1 minus x6, this is the mass flow rate at the 0.1, also at the 0.2. Okay, so that means if you know the mass flow rate at 0.2 and 0.8, then we can again use the energy balance for the mixture. Okay, so that means the total mass flow rate multiplied by H3, that is equal to the mass flow rate at 0.8 into H8 plus the mass flow rate at 0.2 into H2. So by using this energy balance, we can calculate what is the enthalpy at 0.3. Okay, so that H3 we can calculate, and by using the H3 we can also calculate what is the entropy and what is the temperature at 0.3. Okay, because that pressure is equivalent to the intermediate pressure which is given. Okay, so we can get the other properties at 0.3, and then we can again use the same procedure to calculate the state point 4. So 3 to 4s, this is the isentropic process. So enthalpy at 0.4s that we can get, and after that by using the isentropic efficiency of the high temperature compressor, we can get the enthalpy at 0.4. Okay, so by this way we can get the enthalpy of all state point of this cycle. Okay, then we will go to the performance parameter. Okay, so like your what is the cooling capacity. So cooling capacity for this cycle can be written as m dot, let's say this is m dot is the total mass flow rate in a condenser. So m dot into 1 minus x6, this is basically represent the mass flow rate in the evaporator. Okay, so m dot into 1 minus x6 into h1 minus h9, this is represent the cooling capacity for this cycle. So this cooling capacity also we can write by in this form, that m dot into h1 minus h5. Okay, so h1 minus h5 plus h6 into h8 minus h1. So basically the in this equation we can see that the h9 also equal to the h7. Okay, and if you replace the h7 by using the h8 and h5, okay, if you replace that h7, that is equal by the h8 into a and h5, so because the h5 is equal to h6, so the h5 equal to h6, that is equal to 1 minus x6 into h7 plus x6 into h8. Okay, so from this equation if we replace the h7, and then we can ultimately use we can get this equation. So what is the importance of this equation? So basically if we want to compare with the basic cycle, then we will see that the expansion process, that will basically the from the condenser pressure to the evaporator pressure. So if we expand the process that 5 to 6 up to the evaporator pressure, so basically that is the H5 is basically the inlet enthalpy of the evaporator. So H1 minus H5, this is basically represent the enthalpy change of evaporator in case of the single stage system. Okay, so that's why the m dot into h1 minus h5, so h1 h5, that is basically represent the cooling capacity for the single stage system. So plus we are getting the h6 minus h6 into h8 minus h1. So if you see the pH diagram for this system, which I have discussed in the previous slide, so we can see that the h8 enthalpy at 0.8, that is always higher at as compared to the enthalpy at 0.1. So in general that h8 minus h1, that is positive. Okay, so although this enthalpy difference may not be very high, but that is positive quantity. So that means the h6 into h8 minus h1, that is always positive quantity. So that means if we compare with the basic cycle, single stage cycle, then we will see that the cooling capacity of the system, that will be higher. Okay, here as compared to the cooling capacity of the basic cycle or single stage cycle. So the cooling capacity will be increased by using the two stage compressor with flash gas removal. Okay, then if you see the compressor work, then we will see that for the first compressor work is m dot into 1 minus x6 into h2 minus h1, and for the second compressor h4 minus m dot into h4 minus h9. So if you, let's say if you consider that the same mass flow rate for the basic cycle m dot as well as this modified cycle, so that means the h4 minus h9, m dot into h4 minus h9, that will be similar, but if we compare with the basic cycle for same mass flow rate, so obviously for the basic cycle, if you extend the process 1 to 2 up to let's say the 4 dash, Okay, so obviously that H2 m dot into H4 dash minus H2, that work is always higher as compared to the m dot into H4 minus H3, because that is the same reason that the slope of the isentropic line are different for both the cases. So that the if you compare with the basic cycle, so for the second compressor work, that is significantly lower, that is lower as compared to the, if you compare with the compression in the first compressor, if we extend the process onto 2. Okay, so that part is also, second part will also lower, and for the first part you can see that the m dot into 1 minus x6. So m dot into 1 minus x6, that is always less as compared to the m dot into 1 minus x6, and h2 minus h1, that is less the same. So that means the m dot into 1 minus x6 into h2 minus h1, that is always lower as compared to the m dot into h2 minus h1. Okay, so that means the m dot into 1 minus x6 into h2 minus h1, that is lower as compared to the m dot into h2 minus h1, and also the m dot into h4 minus h9, that is also lower as compared to the m dot into h4 dash minus h2. Okay, so that means the both quantity will be reduced by using this two-stage compression with flash gas removal. So the compressor work will decrease by using the two-stage compression with flash gas removal. Okay, so the, if you see the COP, so what we have discussed, that the cooling capacity will decrease by using the COP, cooling capacity will increase by using the flash gas removal, and the that compressor work will decrease by using the two-stage compression with flash gas removal. Okay, so as a result, the COP, that is basically equal to the ratio of cooling capacity by the total compressor work. So COP by using the two-stage compression with flash gas removal, that will improve. Okay, so we can summarize our discussion by this way, that the cooling capacity, that will increase by using the two-stage compression with flash gas intercooling. Okay, that we have already seen. Okay, by analytical expression, and that also we can get easily by using the any numerical calculations for any refrigerant. Okay, so this is the fact that the cooling capacity will decrease. Okay, although that the cooling increase and cooling capacity increase, and that increase may be depending on the values of percentage increase of cooling capacity, that may be depending on the different refrigerant. For the different refrigerant, different value we can get, but for all the refrigerant we can see that the cooling capacity will increase. Okay, then compressor work will decrease, that also we have seen by the our previous analysis or previous discussion in the previous slides. Okay, so if you do any numerical calculations for any refrigerant, and if you use the two-stage compression with flash gas removal, then also we will see that the compressor work, that will reduce by using the two-stage compression with flash gas removal. Okay, so due to the increase of cooling capacity and the decrease of compressor work, the COP of the system, that will increase. Okay, so COP of the system will increase by using the two-stage compression with flash gas removal. So although for the different refrigerant, the improvement values of the cooling COP may be different. Okay, so and we have already seen that, so basically for this system also, the outlet of the low temperature compressor or low pressure compressor, that means state point 2, that will be basically, that refrigerant will be again intercooled. Okay, or that is cooled in a mixture. Okay, so we are getting the state point 3. Okay, so then the second compression is occurs from the state point 3 in a second compressor. So by as a result, we will see that the outlet temperature of the second compressor or high pressure compressor, that is lower. okay, as compared to the discharge temperature which we can get from the by using a single stage compression system. Okay, so by using this type of modifications, okay, modification, that means the two stage compression with the flash gas removal, then the cooling capacity will increase, compressor work will reduce, and cooling that cooling COP that will increase, and the compressor discharge temperature that will reduce. So what I have already told that the main purpose of multi-stage compression is both the reduction of compression discharge temperature and also the compressor work. Okay, and apart from also we are getting the various advantages by using the two-stage compression with flash gas removal. And another thing is that the improvement of compressor efficiency, what I have discussed in the previous lecture. Okay, so the isentropic efficiency of the compressor, that is depending on the pressure ratio of the compressor. Okay, so higher pressure ratio, that will give the lower isentropic efficiency. Okay, so isentropic efficiency of the compressor, that decreases with the increase in pressure ratio. Okay, so for this system we are using the two compressor, and for the both compression we are getting the pressure ratio that is very less as compared to the compressor which can be used for the single compression system. Okay, so due to the lower pressure ratio in the both the compressor, the isentropic efficiency of the compressor, that will be also reduced. Okay, so that means if we want to compare the single stage compression system with the two stage compression system, then if you use the isentropic efficiency of the compressor which is related to the pressure ratio. Okay, so that means if you want to use, if you use some correlation based on the pressure ratio of the pressure, based on the expression of compressor isentropic efficiency based on pressure ratio, then we will obviously see that the isentropic efficiency for the two stage compression system, that is higher as compared to the isentropic efficiency in a single stage compression system. Okay, so that means that due to the due to the improvement of the compressor isentropic efficiency of the two compressor, so again we can get some compressor work reduction due to the improvement of compressor isentropic efficiency. Okay, so for this case also two type of effect we can get during the compression process. One effect is related to the temperature, okay, or the density of the density during the compression process. Okay, so due to that reason we have already discussed that your compressor work, if you assume the isentropic process, then your compressor work will be reduced by using the two stage compression. And another effect is due to the increase of isentropic efficiency of the compressor. Okay, so due to the increase of isentropic efficiency of the compressor in a two stage compression, again that will give the reduction of compressor work due to that. Okay, so due to these two effects, ultimately we will see that your compressor work that will be reduced, okay, maybe significantly reduced by using the two stage compression with flash gas removal. Okay, so these are the various advantages we can get by using the two stage compression with flash gas removal. Okay, so then ultimately what I have already told that if we use the two stage compression with flash gas removal, your cooling capacity will improve. Okay, so now I have already told that for the different refrigerant, the improvement of cooling capacity may be different. Okay, so and also in the previous lecture I have already told that the variation of cooling COP for the two stage compression system with respect to intermediate pressure, that variation may not monotonous. So basically we will increase the intermediate pressure, then the first compressor work will increase and second compressor work will decrease. Okay, then the combined compressor work, that variation may not monotonous. Okay, so the compressor work will be, total compressor work may be decrease first and then increase. So we may get some minimum compressor work at the some intermediate pressure. So but if we compare with the previous cycle, then on difference we can see that in the previous cycle, that means the two-stage compression with intercooling. Okay, so for that cycle we have seen that the cooling capacity that will be remain same. Okay, but for this case, if we change the intermediate pressure, then the cooling capacity that will be also change. Okay, so for this case the cooling capacity that will change, and the compressor work that will also change with respect to intermediate pressure, and that variation is not monotonous. So the combined effect of this changing of cooling capacity and changing of the compressor work, we can get the this type of behavior, the cooling capacity with respect to intermediate pressure. Okay, so for the I have used the 3 refrigerant, and for other refrigerant that variation that range is not same, because I have taken the same evaporator temperature and same condenser temperature. Okay, so but saturation pressure are different, so that's why the pressure range are same, not same for the different refrigerant. So for this case we can see that the 3 refrigerant which we have used, and although the if you see in term of values, then the that values may be different from different values, and maybe the that optimum intermediate pressure that also may be the different for the different refrigerant. So obviously that range are different, so pressure is also different, obviously. But for all the refrigerant we can see the similar behavior, that we can get some optimum intermediate pressure which will give the maximum COP. Okay, so that is the conclusion we can make by using this graph, and that intermediate optimum intermediate pressure may be different for the different refrigerant. Okay, thank you.